Okay, agree in this part now. Okay, so now let's answer the question before. If in general, if I don't have the benefit, then this sum here, the sequence k equal to 0. I have exactly x omega. But now I have other k, with other terms, the shifted versions. When it's a non-benefit, those shifted versions will add to this term. And equal to this. Not no longer this form. Okay? Is that clear? So let me put now a formal theorem down. And you do need this theorem to do the homework. If x sample of n equal to x of n(t), then I have these two things. But typically people like to go back and replace it by the small omega. Right? Want to replace that, then I can have x as a small omega is equal to, so now I have to put 1 over t summation now in k, go from minus infinity to plus infinity, x of, now I have to do that replace, so that small omega plus 2k pi over big T here, and that is the formula. So that is the theorem of supreme importance in DSP. Okay. And I show you the derivation, you will do need this formula in your homework. Alright, any question on this? So you see that a very simple calculus and with some intuitive reasoning. Okay. Anyone? Any questions? Alright, so let me show you some figure here. A sample. And sampling that signal, we want to understand in frequency domain, what does it do? Well, you have this signal that says so that in the spectrum of the signal, up to that capital omega. And then that little formula I have here, the signal equal to summation of the original spectrum plus all this term. Right? The term that take this is shifted by 2 pi over t. This 2 pi over t. Okay? And I keep going, right? So I get more and more. So the signal in sample version having all of these things repeated. Okay. And Koda's way you say, if early on I know that the thing died exactly at pi over t, I will be happy because I can take this part and go back to the original signal. If not, so that is a nice thing because these terms they don't add on top of each other. But now, if we do have the case where I sample too slowly, what happened here is this triangle now get too close to each other. And what went well, then this part here now get added up, not just right in the frequency domain. And in the frequency domain, the Fourier transform of the continuous signal going to be added together, all of this alias version, so k equal to 0 ahead of this. When k equal to non-zero, all of these are alias version, and they just add on top of the original. Okay. So that is a part of the sampling. Now, we want to do reconstruction. Reconstruction now. I want to do reconstruction now is I can have this signal. So now I'm going to do a reconstruction. Is I have a signal. Imagine now that I do have a signal in the continuous domain. And I do have a signal in the continuous domain. So the sequence of number stored in my computer. Now I want to bump it out to a loudspeaker, right? At the music. That means I need to have a continuous domain signal. So having that, maybe yesterday we had simply, draw the line across here. Or a very simple operation people may. Okay, so people want to have a signal. So a simple version, maybe I take that sample, I hold it for a while, take a signal, hold it for a while, take a signal, hold it for a while, and so on. And the interval from here to here, because originally from here to here is one step, and now I want to make this a T step. I go back to my original signal. So that one way. But in general, I could simply put a simple pulse signal here. So same pulse, but I just raise them a different height and put them. So suppose that now I'm going to take the signal. Given xn, so this is a discrete signal. Given that signal, now I need to construct the signal y of t. I'm going to, and there's a lot of devices to do. This simple device is simply put the box. So given that, I'm going to construct this equal to summations in n of x of n. And then I have a pulse. So call that is P of t minus mt. Okay, so this summation now goes from minus infinity to plus infinity. So in this simple example, this pulse simply go from 0 to 1 and have 0 to t and have 1 here. So that where it is where pt equal to that. Can you imagine that, right? If I have a pt equals 0 to t here, so that gives me the first one. And then the next one, I simply have to shift it. Right? So that, for example, this is p of t, and this is p of t minus 1 time t, and so on. Okay, can you see the pulse going from here to here with this? Okay, so that is my signal. Now again, remember I can try to see this is what happened in time. And I want to know what happened in frequency domain. So now I want to start, when you go together in a group, right? You want to go together in a group for 5 minutes. Alright, give you a break now in class, but I wanted to do something. So put out a piece of paper, and what I do want you to do now is this thing now, I can compute the Fourier transform of this. Okay, I do know the Fourier transform of this. This thing now, I can compute this Fourier transform of it, and this thing here have the Fourier transform of it as well. And we do want to know what is the relationship between the three guys here in frequency.